Okay, so now we have seen that in the classification equipments, we have seen the important one, that is terminal velocities, by which equal to the settling particles velocities or diameters and densities, like that. Okay, so now very important equipment in this is theory. It's a classification equipments. Classification equipments. So theory of centrifugal. So very important. Theory of centrifugal sedimentation. Theory of centrifugal sedimentation. So here there will be a basket. Here only I'll draw it. So trajectory and this is the bowl mill and this is the axis of the bowl, central axis of the bowl. The feed is inputted here, and from here to the axis it is R1. The initial material, initial particle from the axis is RA, and upon the final, upon where it has to be reached here is RB, and from the wall, bowl wall, up to the center location is R2. Okay, this is the height of the bowl mill. Okay, so what is our, okay, what do you understand by this? Okay, what do you understand by this? And same height has to be there here, right? Right. So what is these two things are? It is nothing but, see, one, I'll just draw it here for your convenience. So actually this is the centrifuge. Okay, this is the centrifuge. Then if you put liquid in it, okay, and the particles will classify the particles. Classify means will separate the particles by the known diameters by centrifugal sedimentation. Centrifugal sedimentation means by centrifugally the particles will get sedimented. Okay, suppose the particles are there and the liquid is there, then what you do is you, with the help of the motor, what you do is you circulate this. Okay, so I'm sorry, you rotate this. Okay, you rotate this centrifuge. It's called as centrifuge. You rotate the centrifuge. If you rotate the centrifuge, what will happen? Because of the centrifugal force, yesterday we have seen that ball mill, the grinds are attached to the wall, like that. With this centrifugal action, what will happen is this liquid which is present here, okay, will be sticking to this like this, and there will be a vortex formed here. Vortex means the distance, vortex means the gap. Okay, because of the high centrifugal force, the liquid will be thrown to the sides and it is attached with the bowl. So now this is shown like this. This is shown like this. Okay. So now this particular diagram is the centrifuge is in a rotating one, and already the liquid has gone to the side, and in between there is a vortex. Vortex means an empty space, like so. That is the imagination what you have to make it. Okay. Now what is R1 here? What is R1? And R1 is from the axis, central axis. What is the distance of, or the thickness, or the radius? We'll call it as a radius from axis to the thick layer, R1, and the particle which is present here, which we want to remove, the particle which we want to remove of that particular diameter. Okay, classification by diameters or radius using centrifugal filtration. So this RA is from the axis to this particular particle, which initial state of the particle. Then after rotating it, it finally reaches to this particular point, that is RB and R2. So what we do is, these particular particles should reach to certain point, and then these particles should touch the wall, thereby settling through the wall. Okay, so that is the idea. Okay, it should not be, then this is an open one. Actually, I told you, this is an open one. Means if you fast rotate it, what will happen? There is a chance that the particles may spill out of it. The particles should not go out, only the liquid may go out. Okay, the particle should strike the wall. The particles which are present here should strike the wall, and then that will be passed through this, and we have a certain space here to remove the particles. Like that, we will remove the particles through the sedimentation. Particles of required size. See, so many particles will be there here, a mixture will be there, in which we want to remove our particles. So that is a beautiful concept of this centrifugal sedimentation. Are you clear now what we are talking here about? RA, RB. RB is this is the final point. From once it reaches here, it will strike the wall and it will be coming out. Then R2 is the final. R2 is this. Okay, if the particle reaches to the R2 or to this one, we'll see what exactly it means. Fine. So in a sedimenting centrifuge, in a sedimenting centrifuge, a particle of given size, is removed from the liquid, if sufficient time is available. If sufficient time is available for the particle to reach the wall of the separator ball. This is very, very important. The wall of separator ball means R2. R2, it has to reach to R2, separator bowl. Okay, to reach. This is the concept available for the particle to reach the wall. Once it strikes the wall, what will happen is it will come out of it and it will be under the influence of that, and it will drop down through that, so that we have removed that particular diameter of the particles. So that is the beautiful concept of this one. So in the so many varieties, or in the so many in the mixture, large many diameters, we can remove our required diameters or radius. Okay. If it is assumed that the particle is at all times moving radially at its terminal velocity, the diameter of the smallest particle, that should be just be removed, can be calculated. So that is a beautiful concept of this centrifugal sedimentation. If it is assumed that the particles at all the time moving radially and its terminal velocity, the diameter of the smallest particle that should be just be removed can be calculated. Number one, the feed point is at bottom. The feed point is at bottom. So we will be feeding from the bottom, and liquid discharge at the top. See, the feed is at the bottom. The feed with the particles will be at the bottom, and the liquid at the discharge. So our particles should not get carried away from the top. Number two, assume that all the liquid moves upward through the bowl. All the equipment moves through the bowl at a constant velocity. Carrying solid particles with it. Number three, a given particle begins to settle. At the bottom of the bowl. At some distance in liquid is RA. A given particle begins to settle at the bottom of the bowl at some distance in the liquid RA. Its settling time is related. Its settling time is related. Its settling time is related to the residence time. To the residence time of the liquid. Residence time of the liquid in the bowl. At the end of this time, let the particle be at a distance. Let the particle be at a distance RB from the axis of rotation. A given particle begins to settle at the bottom of the bowl at some distance. The liquid is RA. Its settling time is related to the residence time of the liquid in the bowl at the end of this time. Let the particle in the bowl at the end of this time. Correct. Let the particle be at the distance RB from the axis of rotation. Okay. So now let us see what exactly happens here. Very interesting analysis can be done. If RB is greater than R2, what is RB? RB is the radius of the particle which has reached to this particular place. If RB is greater than R2, so what happens to the particle, you tell me? The particle leaves the bowl, correct? And the particle leaves the bowl with the liquid. Correct? If RB is greater than R2, what is our concept is our particle should strike the wall. Our particle should strikes the wall. Means what is now? If it is striking the wall means our RB should be equal to R2. So if RB is equal to R2, then it is deposited on the bowl wall. It is deposited on the bowl wall and settles and removed from the liquid. Settles and removed from the liquid. So that is a concept. That's what I told you, that you should rotate the centrifugal sedimentation in such a way that our particles, the radius, the final diameter or the radius of the particle from the distance, you can call it as a distance. Instead of calling as a radius, you can call it as a distance. So if you take the distance from the axis to the final point of that, it should strike the wall, correct? It should not, if it is greater than this, it will leave. It will go to the overflow. So it should reach the wall. It should strike the wall. So that what will happen is, once it strikes the wall, then it will settle by its own velocity. That is called as, its acceleration will be zero. So what is happening, once it is in the centrifugal action, its acceleration will be there. So it will be floating in the water. Then once it strikes the wall, what will happen is, the acceleration will be 0 for that. Okay, and then the particle settles by its own. That particular, as you know that, this is called as terminal velocity. Terminal velocity means where the acceleration of the particle becomes 0 and it settles by its own weight. Let us say it settles by its own weight. That is called as, at what velocity it settles by its own weight is called as, or density is called as, the terminal velocity. Okay, so once it strikes the wall, what will happen is, technically we can talk it like, it is away from, suppose you are in the vicious circle, immediately you are thrown to the wall, then what will happen? Your acceleration will be, you are along with that, say the velocity, you are there with that, but the acceleration will become 0, and then the particle will, let us say the particle has strike the wall, the particle will be settling through the wall by its own velocity. So, if the particle, again these are the assumptions, okay, if the particle settles in the Stokes law, if the particle settles in the Stokes law, in the Stokes law range, the terminal velocity ut is equal to omega square r into rho p minus rho by 18 mu dp. So this is the general one, what we have discussed earlier. Since ut is equal to dr by dt, since ut is equal to dr by dt, then dt is equal to 18 mu by omega square rho p minus rho d square p into dr by r, okay, integrating between the limits, r is equal to Ra. When r is equal to Ra, initial at time is equal to 0. Initial point, Ra, the distance of the material or the particle, required particle from the axis, initial time. Integrating between the limits, when the distance of the particle is equal to Ra at time is equal to 0, when it is not moving, then and r is equal to Rb, at time tt gives tt is equal to 18 mu by omega square rho p minus rho d square p ln of Rb by Ra. If you integrate it and put the limits, you will be getting this equation. Residence time tt, is equal to the volume of the liquid in the bowl in the ball V divided by the volumetric flow rate, divided by the volumetric flow rate Q, then the volume V equal to pi b R2 square minus R1 square. So substitution in equation 3 gives Q is equal to residence time Tt is equal to the volume of the liquid in the ball V divided by volumetric flow rate Q. So Tt can be written as V by Q, meter cube per meter cube second, correct. So have you understood this? I'll just write it here. It is Tt can be written as V by Q. What is V? Meter cube. And what is Q? Volumetric flow rate, meter cube per second. So this will be the second. So what we are now converting, Tt is equal to V by Q, then V can be written as, if V can be written as rho pi b, if V can be written as pi b, if this V can be written as pi b R2 square minus R1 square, then the equation becomes Q is equal to pi b omega square rho p minus rho d square p by 18 mu R2 square minus R1 square divided by ln RB by RA. So this is 4. Now cut point diameter can be defined as the diameter of that particles which just reaches one half of the distance. The one question may be asked here in this. One half of the distance between R1 and R2. One half of the distance between R1 and R2. That is called as R1 and R2. This one, R1 and R2. One of the distance, cut point diameter can be defined as. So a question may be asked when the cut point diameter, one half of the distance from R1 and R2. If DPC is the cut diameter, a particle of this size a particle of this size moves a distance y is equal to r2 minus r1 by 2, correct, during the settling time allowed. During the settling time allowed. If dpc is to be removed, now if dpc has to be removed, then it has to reach to wall. That's all. The concept is the material, whatever the diameter of the particle, it has to reach the wall so that it will be away from the centrifugal force. So once it strikes the wall, its centrifugal force, it will be away from the centrifugal force. That's the concept. So what he means, during the settling time allowed, if dpc is to be removed, what should we do now? It has to reach in available time. RB is equal to R2, correct, and RA is equal to R1 plus R2 by 2. That is a condition, because the definition of cut point diameter is that. Then equation becomes, see how interesting it is. The equation becomes QC is equal to pi b omega square rho p minus rho d square pc, cut point diameter, by 18 mu R2 minus R2 square minus R1 square ln of 2R2 by R1 plus R2. The QC means the volumetric flow rate corresponding to cut diameter, where QC is equal to volumetric flow rate corresponding to the cut diameter, Okay, right. If the thickness of the liquid, that is very important. If the thickness of the liquid, if the thickness is good, then only we can talk more about it. Okay, thickness. What is the thickness? Thickness is this. Correct. This now we have come to the major one. If the thickness of the liquid layer, is small compared to the radius of the ball. R1 is equal to R2. Equation 5 becomes, it's very, very important, becomes indeterminate. A question may be asked on this. Indeterminate means we cannot solve the equation. Means infinity. Indeterminate means infinity. Because if there is no thickness, what will happen if the thickness of the liquid layer is small? So it's very, very important. These questions only the gate, the person will be asking you the questions, because this is very, very important, because we have to analyze as an engineer. Okay, this is very important in this derivation. If the thickness of the liquid layer is small compared to the radius of the ball, R1 to R1 and R2, there is no distance between R1 and R2, then Q becomes indeterminate, means this becomes 0. If this becomes 0, then this becomes the infinity. When R1 is equal to R2, it becomes the infinity. So, to get this particular equation, the thickness of the layer should be good. That is the fundamental concept of centrifuge. The centrifuge fails, or the centrifugal sedimentation fails, when there is no There is no appreciable, please use the word called appreciable thickness. So there should be good difference between R1 and R2. That is the main concept of centrifuge. Okay, that's what I want to highlight. Because of that, I have derived all the things. So it's very, very important. The formulas are not that important for the gate. For the gate, these particular points are important. For academics, maybe the formulas are important. For the gate, these particular points are important. Now, by using, we are coming like a story. Now you can clearly understand, if R1 is equal to R2, there is no appreciable thickness here, then we cannot, then there is, the equation QC will become the indeterminate, or QC5. This is equation 5. This one is the equation 5. This equation 5 becomes indeterminate. However, settling velocity, the settling velocity may be considered constant. And given by the equation, ut is equal to d square p rho p minus rho omega square r2 by 18 mu. Let the thickness of the liquid layer be S, and the settling distance for particles of cut dpc, means cut point diameter, be S by 2, then ut is equal to S by 2t. This is another very, very important. S is the thickness and the time. So, okay, that is meters per second. It will become a meters per second. Then it will become the settling distance of the velocity. Then ut will become the terminal velocity of that particular material, where tt where Tt is the residence time, where Tt is the residence time given by, where Tt is the residence time given by Tt is equal to V by Qc. So combining 4 and 8, combining 4 and 8, combining 4 and 8, combining 4 and 8 and solving for QC, and solving for QC, we get QC is equal to 2V d square P rho P minus rho omega square R2 by 18 mu. QC is equal to 2 into V d square P rho P minus rho omega square R2 by 18 mu. So this is the final equation. See how beautiful the concept is about. Okay. So now, however, the settling velocity may be considered constant and given by the equation. So, and let the thickness of the liquid layer be S and the settling distance from the particles of cut dpc be S by 2, ut can be, and equation 4 and 8. What is equation 4? Equation 4 is this: R2 square by R1 square ln of RB by RA. Then dpc, combining 4 and 8 and solving for QC, will get 2V d square P by rho P minus rho omega square R2 by 18 mu. Okay. So this is the beautiful concept of the bowl centrifuge. Okay. Yes. So let us solve the gate problems on this. So let us solve the gate problems on this. Gate 2007. Gate 2007. In the Stokes law regime, the terminal velocity of particles, for centrifugal sedimentation is given by ut is equal to omega square r rho P minus rho. He has given, okay. See how good he is. dP d square P by 18 mu, where omega is angular velocity where omega is angular velocity, r is the distance of the particle. R is the distance of the particle from the axis of rotation. And rho p is the density. Rho p is the density of the particle. Rho p is the density of the particle. Rho is the density of the fluid. Rho is the density of the fluid, and dP is the diameter of the particle, and mu is the viscosity of the fluid. See, all the things here is explained to us. Yes. So, in a bowl centrifuge, centrifugal classifier operating at 60 rpm with water, mu is equal to 0.001 kg per meter second. The time taken for a particle dP is equal to 0.0001 meter. Specific gravity is 2.5 in second. The time taken for a particle in second to transverse means travel. Transverse a distance means travel a distance or moved a distance of 0.05 meters from the liquid surface. Is A 4.8, B 5.8, C 6.8, D 7.8. Okay, so he wants to know the time. In a bowl centrifugal classifier operating at 60 rpm with water, mu is equal to 0.001. The time taken for a particle dP is equal to 0.0001 meters. SPG is 2.5 in second to transfer a distance of 0.05 meters from the liquid surfaces. So means if you just draw the bowl centrifuge here, this is your axis, okay, and then the main, from the axis it is 20 centimeters. From the axis it is 20 centimeters. Is it right? So in a bowl centrifugal operating at 60 in a second to transverse. Okay, he has given the picture also. Okay, he is giving the picture also, yes. So this is the bowl mill, he has given it, bowl centrifuge, and he says it is the surface of the liquid is the axis of rotation. This is all we know, right? So he has given up to here, this is 20 centimeters. So according to us, what is this? This is R1, correct? R1 is 20 centimeters. R1 is 20 centimeters he has given. And in a second to transverse a distance of 0.05 meters from liquid surface is. So he says that in a second to transfer a distance of 0.05 from the liquid surface. So 20 centimeters, then R1 you can take it as RA here, and then TT is equal to 18 mu by omega square rho P minus rho D square P ln of RB by RA. So here you can take it as R1 as RA is equal to 20 centimeters. So if it is traveling, means RB. Transverse, it says transported, means travels. RB 0.05 meters. 0.05 meters means 5 centimeters. Okay, so 25 centimeters. This is what we have to understand. Okay, so he has given clearly that transverse a distance, right, 25 centimeters. Then just substitute the value, that's all. 18 into viscosity 0.001, okay, divided by omega square. Omega square is omega square. Omega square, how you calculate? What is omega square? Omega square is 2 pi n. That is 2 pi radians. 2 pi n by 60. Correct? Omega. Omega is equal to 2 pi n by 60. Okay. So omega is equal to 60 rpm is given. In a centrifugal classifier operating at 60 rpm is given. So that is 1 rps. 1 rps is equal to 2 pi radians. Okay, so just substitute 60 here. So actually just substitute here. N is the RPM, correct? 60 RPM. N is 60 RPM. Okay. Then RPM, 60 RPM means 1 RPS, correct? 1 RPS. So omega will be 2 pi radians per second, or just substitute 2 pi 60 by 60. 60 will get cancelled. So it will be 2 pi radians per second. This is what I am writing, 2 radians per second. So omega is 2 pi. So 2 pi square rho P minus rho. Rho P minus rho means 2500 minus 1000. Okay. 2500 is a specific gravity given, and water is told the water, so we can take as 1000. Okay. Then dp square is 0.0, please be careful, 0.00301 0.301 square. Please be very careful with this. Ln of 25 by 20. So you will be getting as 6.782 or 6.8 seconds. So the answer is C. So that is what the understanding here about. Okay. So now this beautiful concept what we learned is centrifugal sedimentation problems. Okay. So we'll continue in tomorrow's session. Okay, hope you enjoyed today's one. I have enjoyed really well, because centrifugal sedimentation is a beautiful concept of separating the particle for the known time, okay, using the centrifugal filtration. Thank you.